of samples we increase and we get the means from those samples as
No,
well.
no.
So
What?
the means are closer to each other
No,
and we
no.
will get this normal well.
No, that's not right. If you take a sample of size, suppose think of just sample of size 1 from a population, call it x1. Sample of size 2, size 1. I will take another sample of size 1, call it x2. Take another sample of size 1, call it x3. Then average them. Right? Like that you can take many such samples of size 1 and get many such averages.
Right.
The distribution of these averages will be normally distributed as the sample size becomes larger and larger and larger.
Across the population mean.
The population mean has nothing to do with this. It's the distribution, no? What we're looking at the shape of the sample. Right? Okay, now, so look at this picture. Okay? So look at this picture. Now, say I'm taking, right, so look at this. Yeah, so this is a picture of a normal distribution by default, by definition, because that's how I've generated my data. Right? Okay. Now, let me ask a question. Suppose I drew a straight line at -10. Right? So suppose I did the following. Okay? I did the following. I said, so I did a line at -10. I want to find out what is the area of this curve to the left of -10. I want to find out the area of the curve to the left of -10. How much of the area of the curve is to the left of -10? If I think of the area of the entire curve as 1, then let me find out what is the area to the left of -10. Okay? So I must ask the question. Okay? So there is a command in R called p-norm. So if you do this, what does the command p-norm tell you? P-norm tells you what is the probability, okay, up to a point q. So if I wanted to ask that question, what I'll do is, I'll answer this question as follows. The command pnorm, so it's a pnorm, okay, -10. What is the mean of my distribution? 5, right, and 6. So it says area to the left of -10 is 0.0062096665 of the distribution. Area to the left of -10, that is, it says the area of the distribution to the left, if this whole area is 1, then area to the left of -10, okay, is 0.0062096665. Okay?
This is proportion of area?
No, it is just area. Actually, the whole area is 1. Right. So, if the whole area is 1, the area to the left of -10 is 0.0062096665. In other words, 0.0062096665 is the probability that a normally distributed random variable with mean 5 and standard deviation 6 takes a value less than -10. Yeah? So 0.00000625 is the probability that a normally distributed random variable with mean 5 and standard deviation 6 takes a value less than -10. Right? So now let me ask you a question. I did this. okay, minus 15, right? And then suppose I ran this, yeah, and I got this answer. What does this number stand for? 0.0042900603.
Probability less than minus 15.
Once again, the area
Around
to the left.
Yeah, so it is the probability that the normally distributed random variable with mean 5 and standard deviation 6 takes a value less than 15.
So this is standard deviation or variance?
Standard deviation.
And previously it was
No, it
variance.
is the standard deviation.
Okay, it's
By the R syntax, it is standard deviation. So if I change this value, for example, if I change this value from say 2 to 4, right, the number has changed. It will become 0.000006 times 0. This e raised to minus 7 means that you need to remove the decimal, take this decimal 7 places to the left. E raised to minus 7 means that you take the decimal 7 places to the left. So it will become 0.2 and then 0.0. So 0.000060, right? So obviously it changed from here to here. Why is this changed? Can you tell me why? Why?
Because as you move to the left, the area under the curve reduces.
But I have not moved to the left. See, my previous graph,
So
when I changed the variance, so
the
this was
spread has-
minus 50,
okay.
right? When I changed the
Spread
variance,
reduces.
the spread of this curve declined. No? So the area to the left of minus 15 also declined, right? If I increase the spread of this distribution, suppose I were to increase it instead from 16 to say 20, right? Then 0.1158655 has increased.
So you said this is the probability of getting a number in that
Getting,
area.
it takes getting a number in that range. So probability that so it is 0.15 now. 1586 is the probability that a normally distributed random variable with mean 5 and standard deviation 20 takes a value less than minus 15.
Okay. Probability.
It's a probability, no? It's a probability that a normally distributed random variable with mean 5 and variance and standard deviation 20 takes a value less than minus 15. Right, so one of the things it depends upon is of course what is the standard deviation. Now suppose if I change the mean, okay, this number has increased to 0.22, right, I change the mean from 5 to 0,
Right.
why has this happened?
Left. The curve has moved a little left.
So variance are kept as it is.
The curve has moved
What
a
I've
little
changed, I've changed the
left.
mean, no?
Mean.
I've changed the mean. So what has happened? See, previously this was the line, I've reduced the mean, so the whole curve has shifted here, so this area has increased.
Right.
Sure, is this clear?
Yes, right.
Now this is a very important idea. Because, so what the point I'm trying to drive at is, that if something is normally distributed, we all agree that normal distributions are very important, right? So if something is normally distributed, okay, fine. The probability, okay, of, so basically, if you think of this as I'm sorry, just pardon me, I never got good marks in drawing class ever at school. So, right? Okay. So, if you wanted to find two boundaries, which such that 5% of the distribution to the left of this line, and say the 5% of the distribution to the right of this line, so that 90% of the distribution is between these two lines, right? These two lines would depend upon the mean and the variance of them. If you increase the variance, then obviously area to this side and this side will increase. So these will move further in. If you decide that I just want 5% to the left, 5% to the right, and if you press this, this whole thing will spread out. So so you have to move these lines, right? Also, if you shift the whole curve like this, then of course those locations which contain 5% of the area change.
So sorry, you're saying if the standard deviation increases, then the tail becomes longer.
The tail becomes longer. So these lines will have to move outwards correspondingly, right? Because they'll have to contain. Sure?
Yeah.
Okay. Right. Now, so let's think of why is this important. Okay, this is practically, so let me think of practical example where I can, let me think of a fairly bizarre example. It will keep you awake on a Sunday afternoon, right? Okay, suppose for some reason, suppose you're working for the wildlife department, right? Suppose you're working for the wildlife department. Suppose you're working for the, there is a forest in Uttarakhand, and that forest has some elephants. Right? There is not, I think that's the only place in North India where there is that Rajaji National Park. There are elephants, right? Okay. Now,
Jim Corbett.
Jim Corbett. So let us think of the Rajaji National Park, right? Because there is a highway which goes right through Rajaji National Park. There is a highway which goes from Haridwar to Rishikesh and onwards, and which divides the national park into, So there is continuous traffic. Elephants are skittish animals, so they can't cross over. Because if elephants can't cross over, then they can't access their food and everything. Elephants need a lot to eat, so they need to have a lot of place. And if they can't cross over, then they might fall ill and so on and so forth. So the forest department is worried that because of this continuous traffic, elephants in Uttarakhand are becoming thinner, right? And your job is to identify elephants who are too thin, right? Now, how do you identify whether an elephant is too thin? Right? You can't take BMIs for elephants and right? There's going to be but virtually we're going to do that, right? So you are told that look here, the weights of elephants. The first one tells us that we have data on healthy elephants, right? We have no data on unhealthy elephants because elephants in general have been very healthy in the forest, right? So the weight of healthy elephants, the mean weight of healthy elephants is 5 tons. Right? Okay?
5 tons.
5 tons. And weights of elephants are normally distributed in such a way that 95% of the healthy elephants weigh between 3 tons and 7 tons. So we have a normally distributed population of healthy elephants. Population of healthy elephants is normally distributed. The mean weight is 5, this is 3, this is 7, and this contains 5% distribution, this contains 5% distribution. It's a bell-shaped symmetric distribution. Right? So 3 tons, 7 tons and 5 tons. Now, so you have to just think like this. You assume that your basic assumption is that the elephant that you are going to encounter is a healthy elephant. So you trap these elephants, they fall into ditches, you have a massive crane which picks those elephants up, and then there is a massive weighing machine which gives you the weight of the elephant. Right? So if you find an elephant who weighs less than 3 tons, so you find the elephant who weighs 2.5 tons, right? Then you've got 2 ways of thinking about it. The first argument is to say, look here, the forest department has told me that 90% of the healthy elephants will weigh between 3 and 7 tons. So 5% of the healthy elephants will weigh less than 3 tons. 5% of the healthy elephants will weigh more than 7 tons. Right? So if there are say 20,000 elephants in this forest, 5% of those elephants, right? Okay, which is how many elephants? About 100 elephants do weigh less than 3 tons but are healthy. Now the elephant I have caught is likely to, it's possible that the elephant which I have just trapped is one of those elephants. Because there are 100 elephants who weigh less than 3 tons and still are healthy by the information the forest department has given me. And I could have trapped one of those 100 elephants. Right? Or you could say that look here, there are 20,000 elephants in this forest. Only 100 of them are healthy but weigh less than 3 tons. The chance of encountering only one specific elephant out of this 100 out of 20,000 who keep on roaming around the forest randomly is very, very slim. So, the elephant which I have got, in fact, might not come from this population of healthy elephants, is in fact an unhealthy elephant. Right? So, you got 2 arguments. One argument is to say that given the information the forest department has, the information that I have, 5% of the healthy elephants weigh less than 3 tons. There are 20,000 elephants in this forest. So 100 of those elephants are healthy but weigh less than 3 tons. and the elephant which I have caught is one of those elephants. That is one possible argument. The other possible argument would be, look here, there are only 100 healthy elephants who weigh less than 3 tons out of 20,000. Right? And they keep on roaming here and there randomly. So I would have to be extremely lucky to figure out to get only that one of those 100 elephants. But it's possible that the elephant which I've got in fact doesn't belong to this population of healthy elephants, it's an unhealthy elephant, because there is only a less than 5% chance that a healthy elephant weighs less than 3 tons. And I've got one such elephant. Right? I've got an elephant who weighs less than 3 tons. Right? Now what call do you take depends upon how important it is for you to have healthy elephants. Right? Now suppose the elephants were extremely rare. Right? And for some reason this was the only population of elephants in the world, and if these elephants died, then elephants would become extinct and so on. Then you would say, ठीक है यार, in the first argument ये हो सकता है one of these 100 elephants, but I don't want to take a chance. Right? I will treat this elephant. I will take this elephant to the medical camp and treat that elephant and so on and so forth. And because it might, because the chance that it's a healthy elephant is slender. It could be an unhealthy elephant, an elephant which needs assistance. Right? In which case, you will send the elephant to a medical camp. But if there are lots of elephants really, and elephants are not so important, but transporting those elephants somewhere requires a lot of money and resources, those money and resources can be used better somewhere, right? And elephants are not really that critical, but the money of transporting them, feeding them is very important. You might say, "Chodo yaar, ye ho sakta is 100. Why do you want to incur an additional expense unless you are very, very, very sure?" Right? So what you do with that elephant depends upon these two things. If you take the first line and say it's extremely important to conserve these elephants because they are the only elephants in the world, right? There is no other population of elephants, and if these elephants need to be conserved, so I'm willing to take the chance of being wrong 5% of the times, right? What you're in fact doing is rejecting your basic premise that the elephant that you have got is a healthy elephant, but you're willing to take a 5% chance of being wrong. Because you don't want to really be wrong in a fundamental sense of not conserving elephants properly. So you're willing to take that 5% chance of being wrong in the sense misclassifying a healthy elephant as an unhealthy elephant. Right? And sending that elephant to a repair camp. Right? A medical camp where the elephant is fed good things and so on, and then later on released back into the forest. Right? Now, misclassifying a healthy elephant as an unhealthy elephant is called type 1 error. So you're willing to take a 5% chance of a type 1 error. You're willing to take a 5% chance of a type 1 error in this case. Okay. So what are you doing? You're going to use this rule that if you catch an elephant, if an elephant weighs less than 3 tons, and because elephants are precious, you're not going to take a chance. Any elephant who weighs less than 3 tons is going to go and receive medical treatment. Even if he is a healthy elephant, we are willing to take the chance 5% of the times. 5% times you are willing to go wrong because elephants are extremely crucial things to have. Right, so you are happily going around in the forest with this 3 tons and 7 tons kind of a thing fixed in your head. Whenever you catch elephants, if an elephant weighs between 3 and 7 tons, you let that elephant back again. The elephant gives you an angry look but vanishes in the forest. Right? But if you find an elephant who weighs less than 3 tons, immediately the elephant is corralled into a truck. The truck takes that elephant to an elephant heaven somewhere in Netherlands where they are fed well and all that and kind of a thing. So you are happy doing that. Suppose you are doing this in the forest, and then you meet a classmate of yours in the forest. He is also roaming around in the forest, but he is carrying a net and a small bottle, and there is some liquid in that bottle. So ask him, what are you doing here? He says, no, you see, this forest department has hired me. So what is the forest department hired you for? See, all these are teak forests, no? In this, and this teak forest flower, right? And for the teak forest to regenerate itself, these teak trees have to be pollinated, and they are only pollinated by special kind of a bee. Right, now the forest department is scared that these bees are becoming too thin. So they have asked me to identify bees who are too thin. So I said, how do you identify bees who are too thin? So forest department has told me that the mean weight of a bee is 3 grams, right? The bee weights of healthy weight, the mean weight of a healthy bee is 3 grams, and these bees are normally distributed, and say 90% of the healthy bees weigh between 1 and say 5 grams, right? Okay, so what I do is I catch hold of these bees, I weigh those bees. If a bee weighs less than 1 ton or 1 gram, I know that there is a 5% chance that it might be a healthy bee, but I am told not to take the risk. So this bee, I've got this protein shake which I feed to this bee, and then the bee is released in the forest, right? So this 1 gram, So you envy that guy a little bit because he doesn't have to carry all those, cranes and big weighing machines. He's just walking around with a, So you say bye to your friend and continue your journey, and then you see a friend, you meet another classmate of yours carrying a big gunny bag. He says, now you ask him, what are you doing? And he says, no, I've also been hired by this forest department here, and so by now you start to get on the game. So he says, what animal are you studying? He says, I'm studying porcupines, right? And so what do you do? He said, no, our forest department is worried that the porcupines in this national park have become very thin. So what do you do? He says, no, you see, I've been told that the weight of all porcupines, healthy porcupines, is normally distributed with 500 grams. 90% of healthy porcupines will have weights between 100 grams and 900 grams. So my job is to catch porcupines, weigh them. If they weigh less than 100 grams, I know there's a 5% chance that it's a healthy porcupine, but I'm not taking the risk. So again, porcupines go to Dehradun, where they are all fed nice fruits and everything, and then they are released back in the forest. So slowly you learn that actually your batch and the previous batch and everybody who's passed out in the last 10 years have been doing the same thing all over the world. Right? So some of you are studying squirrels, some of you are studying elephants, some are studying rhinoceros, some of you are studying magpies, right? Some of you are studying earthworms, some of you are studying king cobras. It's a massive kind of a variety. So you said, let's all get together to have a get together. So all of them come. Right? When all of them come, you realize that all of them have information which is specific to a species. Yeah. So you say for our future generations, people who want to study all types of animals, let's create a compendium of this information. So you identify species and you will know what are the limits in order to identify a healthy animal of that species. So it's a kangaroo, there will be limits. If there is an alligator, there will be limits. If there is there will be those limits. So in the future, somebody wants to study alligators, they can study this information. If somebody wants to study moths, they can study this information. Somebody wants to study crows, they can use this information. So you start by making a compendium like this, and you say, okay, I'll be the secretary of your association. You form an association. You are happy to become the secretary of that association, and then you start putting together this compendium, and you realize what trouble you put yourself in. Because birds only, there are more than 10,000 species of birds, and there are subspecies and all that, and mammals and reptiles, and you never know how many there are. Right? So compendium is never getting completed. Right? And you keep on getting calls from members of your association saying that work in Abhi, and they were saying Abhi nahi, nothing, and it is not completed. So you start getting worked by this whole process of this never-ending job which your association of friends has given you. So you start wondering, wouldn't it have been really great if the number here and the number here, instead of differing across species, had been the same for all species. So if a butterfly weighs less than so suppose think of these numbers in general being alpha and beta, and suppose this alpha and beta are common for all species, right? So that if a butterfly weighs less than alpha, you classify that butterfly as too thin. If a giraffe weighs less than alpha, you classify the giraffe as too thin. If a deer weighs less than alpha, you classify the deer as too thin. So you are just wondering, why is it not possible that I cannot have the same number for all species? Right? Wouldn't have been great if there had been the same number for all species instead of having a different measure for all species. Do you think it's possible? Do you think it's possible to have the same number alpha and beta? So that whatever the species of the animal, if that animal weighs less than that alpha, that animal is too thin. If that animal weighs more than that beta, that animal is too fat relative to a healthy population. Relative to a healthy population, it's the same number, alpha and beta. Our numbers will be common across all animals. Do you think it's possible? No?
If we take percentages, then it is a problem.
Scale is the problem. Scale is the problem. But scale is the problem which is the easiest to solve. Right, so look at it this way. Look at it this way. Okay? So think of my elephants, right? So suppose I've got elephants, these are my elephants, right? So I've got 3 elephants. They are weighing tons, right? The 3 elephants